Hi everyone, and thank you to the organisers of the conference for this opportunity to speak today. And thank you to all of you who are listening and watching this video. My presentation will focus on how we can design music pedagogy and learning for inclusion using ski hill graphs, and draws on current research, my PhD research, and previous papers. There is much discussion today about what to include in diverse music education, and progress is being achieved in music history to broaden the curricula. Increasingly, technology is being introduced into music curriculum and music education is moving forward in leaps and bounds. However, the motivation for this paper is initiated by the gaps that remain, which contribute to what is labelled as inclusion. But is it, in practical application, really a form of tokenism? In other words, what more can students learn from studying music from around the world? Don't they already learn about the rhythm and the pitch and the cultural aspects? We should ask, why isn't notation-based meter theory inclusive? And the list on this slide paints a bleak picture: oversimplification of music, underrepresentation of music, lack of acknowledgement of contributions, and cultural appropriation, as is the case, for instance, with the Igbo tribe, Nigeria. The use of notation-based music theory has led to the extinction of traditional music, because this music cannot be discussed with the same level of scholarship as notated music analysed with music theory designed to analyse notated music. The music theory is inappropriate and incapable of scholarly analysis, which is detailed and accurate. The situation is unsustainable, unethical, and unacceptable. Although both students and machines can analyse the onsets of the rhythm and aspects of pitch and timbre through human auditory analysis and the spectral analysis of software such as Sonic Visualizer or Audacity, the information between the onsets, the inter-onset intervals or IOIs, require human listening and human analysis, including the imagination and quantification for accurate and detailed temporal data. And although machines have memory, they lack the capacity to define difference between two onsets of same or similar instruments. Contextual information and cultural features are not addressed, and machines cannot relate pulses and meter in a metric space. It is this last element of music I wish to discuss further: the analysis of the meter. Human listening in combination with machine learning is a powerful pedagogical approach because it brings together the complex and complementary auditory systems of both humans and machine spectral analysis. However, unlike machines, most humans normally experience a small set of pulses and meters, and through a process of active listening, students can be trained to become aware of many pulses and many meters and learn to relate these networks when they map them to the ski hill graph. Much like the visual representation of keys in a circle of fifths, the temporal information of pulse and meter is meant to be represented by time signatures. However, time signatures were developed to represent notation and only one pulse, and traditional meter theory positioned students to experience a disconnect between what they experience as the meter and what they learn is the meter. Teacher, this piece is in 3/4. That means there are 3 crotchet beats in every bar. Student 1. Miss, what does the 4 mean? Teacher, in America it's called a quarter note, and in Australia we call it a crotchet. Student 1. So, Miss, does that mean it is a quarter of something? Teacher, yes, it is a quarter of a semi-breve. Student 2. Miss, didn't you say the longest note, the downbeat, is a dotted minim and that is worth 3 crotchets? Teacher, yes, that's correct. The dotted minim is worth 3 crotchets. Student 1, I heard 3 crotchets. Wouldn't it make the number a 3 instead of a 4? Teacher, the reason we label the denominator as a quarter instead of a third is because it's based on a duple system and it's a convention. This is a hypothetical conversation based on numerous discussions I've had with students over the years. On my LinkedIn profile, you can read more about student exchanges I've had. But however, thankfully, I no longer reply to my students in this way. Notation-based meter theory is problematic for several reasons, such as one, there is a disconnect with what is taught and was experienced. Two, time signatures only represent one pulse, yet the meter theory to explain the time signature defines the one pulse as a group, and that it is the meter rather than a relation between two pulses as a set. These traditional meter theory practices over the years have led to growing confusion about the pedagogy and notation of the meter. Modern scientific research over the past 4 decades has located the meter in the listener, yet teachers generally default to the notation to understand the meter. However, modern meter theory, Richard Cohn 2020, is available for pedagogy to overcome these limitations to account for the temporal experience of embodied acoustics from listening. Cohn's theories are a distillation of meter theory to solve the confusion which has developed about what meter is and how to teach the meter. Since 2015, I've been teaching students the meter through the ski hill graph introduced around 2001 by Cohn to represent hemiolas. Through Cohn's theories, I have replaced notation-based understandings in my pedagogy of meter with a psychoacoustic process to train my students in mathematical music theory. My PhD topic, however, focuses on the first step in this flexible process, the pedagogy and notation of meter through the ski hill graph, in a mixed methods approach using both qualitative and quantitative research for the collection of data. Beyond merely evaluating an approach, the research seeks to scientifically test representations of the meter to contribute novel research about the pedagogy and notation of the meter to include cultural heritage, inclusion, mathematical music theory, and psychoacoustics. Through my collaboration in the project Teaching Mathematics with Music and Music with Mathematics, an international research project based in Sydney, we introduced teaching interventions in schools and in my music studio and produced new and novel research contributions on the pedagogy and notation of the meter, rhythm, and pitch through mathematical music theory. Today, I would like to demonstrate how teaching and notating the meter can work through a psychoacoustic process rather than a notation-based approach. By doing so, my aim is to also provide a solution for teachers limited by time signatures or other methods to assist their students' growing understandings of the meter in an authentically inclusive approach. A particular area of interest in my research is to draw the reader's attention to Western music's traditional approach for the pedagogy and notation of the meter to focus on one pulse, the beat, represented by the time signature, for instance. Most metronomes have one beat. The beat directs the tempo of a piece of music, and students often diligently entrain to this one beat. As the students perform, they project this entrainment to successive parts of the work. However, focusing on our beat is a problem because students actively listening recognize that there are many pulses and meters in most music, and the beat recognized by the time signature may not be relevant for all parts of a piece of music. Like the limitations of a key signature, and music teachers are looking for pedagogical solutions. We don't experience notation when we listen to or hear music, we experience acoustics. The electrical signals travel from the cochlea through the brainstem, become relayed by the nuclei and the thalamus, reaching the auditory cortex, and the mind and body respond. In other words, inclusive music education also requires acknowledgement of evidence-based research in acoustics on the importance and functions of the human auditory system, the largest processing neural network in the brain and body. Acknowledging all pulses and metric levels is an important skill to develop at an early age. Through the ski hill graph, students learn how to identify all the pulses and the meters and map them to the ski hill graph. Duple meters in ratios of 2:1 to the left, and triple meters in ratios of 3:1 to the right. The longer pulses are mapped from the apex and double or triple as each new metric level as they descend. In this way, students visualize their temporal experience of the pulses as sets and subsets as the meters, and they see and hear the many pulses and meters in a multi-pulse metronome. The ski hill graph on the left of this slide is a set of pulses in a relation of 2 to 1, also known as the minimal duple meter, the least amount of meter possible. On the right side of this slide is a set of 2 pulses in a relation of 3 to 1, also known as a minimal triple meter. Most music has a number of these sets of minimal meters at different metric levels, that is, either faster or slower. The ski hill graphs in figure 1 on this slide represent pure duple meter. That is, all the pulses are in 2 to 1 ratio. The meter in figure 2 is pure triple meter in 3 to 1 ratio. In figure 3, a simple hemiola 3 to 2 is represented along with the surrounding pulses. And figure 4 represents a complex hemiola where more than one hemiola was detected by the listener, and mapped here are 3 hemiolas. The ski hill app also features fractions, polygons, animations, and sonifications for each pulse. These features are available in both the ski hill app, MILM 2016, and the stereo metronome, FAN and Calilhanna 2021. Each version has advantages for students, and I generally ask my students to hand draw their graphs first, then map pulses to the ski hill app, but the approach is flexible. From here, students use the data collected to decide on the counting for their pieces, such as to annotate their scores with the B class, a zero-based approach to counting, which is based on the listening experience rather than the notation. Also, to annotate their scores with the counting for the meter based on the depth or number of pulses for each time point, which assists students to make informed decisions about the expression of a piece of music. Observing the pulses and meters in this audio, visual, spatial, and numerical approach assists students to identify cycles in the music they are learning. Each pulse represents a cycle, and together pulses and cycles in 2 to 1, 3 to 1 relation represent meters. With their new data visualized, students can capture temporal information and learn new knowledge about themselves and their music, and have access to music theory to remember each pulse in a compact format with distinct duple and triple metric pathways to assist them to learn a new piece. As a music theoretic instrument, ski hill graphs are a mnemonic device for the listener as an aid to memory for representing the whole metric space, a network of varying complexity, metric structure. Thus, the ski hill graph is particularly useful as an augmented time signature and metronome through which to approach solving problems with notation such as in slide 19, where the meter changes, but the time signature remains the same. Unlike time signatures, the ski hill graph has the capacity to represent all changes in meter through a narrative of mathematical music theory. Through annotating their scores with the beat class and numbers of counting the meter, students make decisions about the expression by making observations about the depth of each onset and how this relates to other extra musical elements such as dynamic markings and phrasing. The approach applies human spectral analysis to identify and relate all the pulses, all the meters, and as structures, along with the structures formed by the pitch, keys, and harmony, which music education normally focuses on. Students then apply the data from the ski hill graph to other representations, such as circle cyclic graphs to map rhythms, and pitch to assist with practicing and learning tricky rhythms through the cognitive fit of analogy. In this way, students note the distances between the onsets and the patterns of scales and chords for voice leading training, such as the hexatonic cycle. Each instrument of Cohn's mathematical music theory forms part of this rich suite of music theory tools for the inclusive analysis of all music. Ski hill graphs are also useful where the notation and sound are disconnected and inaccurately represented, such as in slide 21. Where there are swung quavers notated in 4/4, but the student experiences 12, not 8 quavers. Through mapping all the pulses as fractions, the student can then make informed decisions about how to perform a piece with stabilized rhythms and expression, with zero-based counting through the B class annotated to the score. Because the student experienced a division of 12 for this piece, it is advisable to consider 12-12 as the new time signature for a transcription as heard to correct the mathematics of 4/4 or 12/8 as notational understandings of the meter, the ancient origins of which can be traced, for example, to the traditional music of the Igbo tribe of Nigeria during the slave trade, and is still influencing today through the music of jazz musicians around the world. The ski hill graph also plays an important role in the analysis of metric music, which is not notated, such as evidenced in the traditional Ikorodo music of the Igbo tribe Nigeria. Prior to analysing Igbo music, I had not analysed the meter, rhythm, and pitch for music which was not score-based for academic papers before, and found the task very challenging. However, I had access to the ski hill graph, and I found it was necessary to keep a record of the different pulses as I progressed so that I didn't miss out or forget any part of the metric structure, temporal information, to then discuss and notate the rhythms and pitch which initiated the meters in context to the metric structure. Without first charting the pulses, the analysis would have been oversimplified, or I may have abandoned the task. And sadly, Igbo music is underrepresented, largely because of the absence of music theory, which has the capacity for such analysis, at least until now. This slide represents the psychoacoustic process through which I analysed Ogene Bunch music from the Igbo tribe, Nigeria. I used this same process for teaching my students for their music exams. This slide is a complex hemiola, represents on the ski hill graph from an analysis of Igbo music, Ogene Bunch music, which is also comparable with the hemiolas in the music of Frédéric Chopin, Johannes Brahms, and Antonin Dvorak. For any music where there are complex hemiolas, this is authentically inclusive music education and analysis, and the data from this analysis is comparable with any music from around the world where the same processes are used to analyze music. Until music education becomes authentically inclusive, any apologies or acknowledgements of contributions by governments to people such as the Igbo tribe, Nigeria, although welcome and are steps in the right direction, the gestures should not be merely tokens, rather actively inclusive. This may involve cultural heritage and infrastructure policy change and development to protect and acknowledge the great contribution of the Igbo tribe to the world. Teaching the meter through the ski hill graph becomes an example of evidence-based research for the spatial temporal research, which points to finding best fit of instruments for pedagogy to reduce cognitive load for learning. This also includes converging evidence that mathematics and music are informed by core geometric skills. Time signatures, on the other hand, tell the student what to hear, and the theory limits their understanding and application to their music studies. Thus, traditional music theory is fundamentally flawed, not only mathematically, but also because it cannot initiate inclusivity due to its default to notational understandings removed from the human listening experience. This slide provides a summary of research-based evidence for the benefits of the pedagogy and notation of the meter through the ski hill graph. The following slide provides some of the benefits for learning difficulties and the pedagogy of the meter through the ski hill graph. Thus, this paper provides a solution for the analysis of the meter for all music and demonstrates inclusivity in music education. The approach is based on evidence-based research, indicating its benefits to students, and further testing is underway. Critically, this psychoacoustic approach to analyze the meter has the capacity to enable students to study structures that demonstrate how traditional notation music theory has evolved through Cohn's theories. The theory proposed in this paper is suitable for most teaching styles and is complementary to computational and spectral analysis by machines. Thank you.